Welcome to this IEA webinar. My name is Aitor, and with my colleague Musa, we will be introducing some of the work we do here at the agency on natural gas data. So firstly, we would like to start with some definition and to summarize the role of natural gas in the global energy landscape with some key figures. Natural gas is a combustible mixture of hydrocarbon gases that contains a very high concentration of methane, so it is basically methane. Some years ago, in many countries, it was often regarded as a waste byproduct of oil production. But in the last years, it has become a profitable fuel with an increasing share on the global energy mix. When speaking about natural gas, quantities are usually measured in volumes. As a gas, we need to define the conditions to measure the volume to make sure that we're using comparable figures. For international data collection at the IEA, we use cubic meters in standard conditions, which corresponds to 15 degrees Celsius, 1 atmosphere. The United States is the largest natural gas producing country in the world, and in 2016, they produced almost 750 billion cubic meters of natural gas. In 2016, around 30% of the natural gas produced in the world was traded, meaning that it was consumed in a country where it was not produced. The natural gas trade can happen by pipeline in a gaseous state or by marine carriers after its liquefaction. Europe, for example, imported 1/3 of the gas they consumed from Russia in 2016, which is the second largest producer of gas in the world. On the demand side, despite the multiple applications of this fuel, its main use is the heat and power generation. Again, in 2015, 41% of the global natural gas demand was in the transformation sector. In the last 40 years, the natural gas demand increased substantially. This growth is partially driven by its lower emissions per energy unit burned when comparing it with other fossil fuels. For example, it emits 50% less CO2 than coal and around 30% less than oil per energy unit burned. So now we know that natural gas increased its relevance in the global energy landscape, but what do you think is the share of natural gas in the total primary energy of the world in 2015? Slightly above 20, slightly above 30, or slightly above 40%. So it is 21.6%. So more or less, 1 out of 5 energy units in the world was from natural gas. Even if natural gas demand multiplied ×3 between 1973 and 2015, natural gas is still the third source of energy in the world, after coal and oil. In electricity, its share is slightly higher than for the TPS, it's 22.9, and this is still dominated by coal. At the country level, its relevance changes from one country to another. For example, if we analyze the 5 countries with the biggest TPS, we see that in China and in India, its share is very small, it's around 5%, way smaller than the world average. In Japan, which imports almost 100% of the natural gas they consume as LNG, it's slightly above the world average, it's 23%, and the main producing countries, as expected, have a higher share. So the US have 30%, Russia 51%, and Iran even 66%. To obtain the information presented in the previous slides, we need to collect this data, and this is one of the things we do here at the agency. But before going into deep about our methodology, it is essential to understand the supply chain of natural gas. Firstly, natural gas is produced mainly by extracting a mixture of methane and other gases from the underground deposits. In addition, there are other gases that are mixed in the grid that may come from oil, coal, or renewables, like biogases. We also collect data on infrastructure that connects the production with the consumption. This includes the natural gas grids, both transmission and distribution, the storage facilities for gas or LNG, and the LNG terminals, both regasification and liquefaction. Finally, natural gas is consumed in different sectors, such as the heat and electricity production in the power plants, or the water and space heating production in the residential and commercial sector. Another very important part of the supply chain is the trade, both by pipeline or as LNG, as we commented before. The arrows you see now in the slides connect the different flows with infrastructure. To summarize, all the natural gas produced or imported by pipeline are mixed in the transmission system. The imports of LNG needs to be regasified before mixing them as well generally in the transmission system. Then it goes to the distribution grid, which has a lower pressure, and most of the consumers are connected to this distribution grid, except some big power plants that might be directly connected to the transmission or even to an LNG regasification terminal. Regarding the exports, pipeline exports are directly taken from the transmission grid, and the LNG exports come from liquefaction terminals. Now we're going to see some of these elements individually. For natural gas production, it can be extracted from oil fields, gas fields, or coal mines. The concentration of methane in this extracted raw gas is not very high, so it needs to be treated. Some of the extracted gas is flared, vented, or vented if it's not possible to transport it to a gas treatment plant. Some other is reinjected to enhance natural gas production of the field. The remaining is transported to a gas treatment plant or a purification plant, where its concentration of methane is increased. This process is less complicated than the processing of crude oil in oil refineries, and consists on the separation of the methane from other hydrocarbons, like NGL or oil, and the removal of impurities, such as water vapor, CO2, or sulfur. The resulting gas that comes out of these treatment plants is called the marketable production. This marketable production is what we use at the IEA to quantify the national natural gas production of the countries. In addition, we classify into 3 different categories depending on the origin. So natural gas produced from oil fields is called associated gas, from gas field is non-associated gas, and from coal mines is colliery gas. Regarding natural gas trade, something that may lead to confusion often is the difference between LNG and gaseous gas. It is important to highlight that both are exactly the same product, they're methane. And the only difference is its physical state. To produce LNG, we need to decrease the temperature of the natural gas below -160 degrees Celsius. And this is done because the volume of LNG is 600 times smaller than the one of gaseous gas, which reduces the cost to transport it across long distances. So as we see in the maps, whereas the LNG trade is global, with shipments from Peru to Europe or from the US to Japan, the trade by pipeline is more regional, such as from Norway to continental Europe or from Russia to Europe. Even if the LNG market continued its globalization in 2016, pipelines dominated the natural gas trade with around 2/3 of the global trade. So about the stocks, even if stocks of natural gas do not catch as much attention as oil stocks, they provide a key service to the natural gas markets. On the one hand, because natural gas demand is seasonal. Taking the example of OECD Europe, we can see how the maximum demand in January or during the winter is more than 60 billion cubic meters, whereas in the summer, when it's warmer, this falls between 20 and 30 BCM. It would be very difficult for the supply to follow this demand. So stocks provide the required seasonal flexibility, resulting in a fairly flat supply. As we see in the graph, the red areas are supplied from stocks, whereas the green areas are the stock build during the months where consumption is lower. On the other hand, in addition to this flexibility, there is another important driver to stock gas: the concerns on security of supply. There are many countries that are fully dependent on imports to supply their natural gas markets. Keeping stocks allows them to address quickly a disruption in natural gas supply. And finally, we classify demand into different sectors: transformation, energy, transport, industry, and the commercial and residential sector. Some of the definitions that might not be completely intuitive are the differences between the transformation sector, the energy sector, and the non-energy use within the industry. Some of the definitions that might not be completely intuitive are the differences between the transformation sector, the energy sector, and the non-energy use in the industry. The transformation sector includes all the demand to convert gas into another energy form. This can be electricity, gas-work gas, or hydrogen for hydrocracking. In this sector, we also include the heat that is sold, for example, from a CHP unit. The energy sector includes the consumption to support its operations. For example, natural gas burned for the oil and gas extraction or in a refinery. The main difference is that this gas is burned but not transformed into a different commodity. In the case of a combined cycle gas turbine, for example, the natural gas burned to fuel the gas turbine to generate electricity will be reported under the transformation sector. When natural gas is burned to keep the boiler warm, but the combined cycle gas turbine is not generating electricity, it is reported in the energy sector. The non-energy use refers to natural gas used as a feedstock to produce a raw material that are not energy products. This use often falls in the petrochemical sector. Now, my colleague Musa will introduce the different possibilities to collect data and also explain the structure of the questionnaire we use here at the IEA.
Thank you, Aitor. I'm Musa and I will present the rest of the webinar. Energy data collection and compilation are difficult tasks, but it is vital for making sound policy and business decisions. The objective of having a collection system is to have detailed and reliable energy data, and to facilitate it we need to have a legal basis, which is provided by statistical laws and other national laws and regulation. It's preferred to make reporting of energy data mandatory. The legal framework creates a necessary but not sufficient foundation for energy statistics. We need to establish institutional arrangement to ensure, collect and compile in the most efficient way among all relevant members of national energy statistics systems. We also need to establish a proper reporting and dissemination mechanism, which includes questionnaires compatible with international standards, a network of contacts, and an agreed timetable. We need to allocate proper resources to collect and process the data. We also need to review the methodology, anticipate and adapt the change to meet national and international needs. Collecting any statistic has a cost. We need to know that despite the cost, a lack of quality data ultimately be far more costly than data collection and associated activities. A balance between the efficient use of resources and collecting what is necessary must be struck. What is necessary will depend on the needs of data users. However, not all the needs will be possible to meet. It's important to look at the change in the energy sector and to limit the collecting by cooperation with relevant government agencies. Challenges. In view of the role importance of energy statistics, one would expect basic energy information to be available, reliable, and timely. This is not always the case, and there are several reasons behind this. The liberalization of the energy markets, for instance, have a two major impact on statistics. First, while in the past we could obtain detailed information from a single national company, now we need to send hundreds of surveys to the companies to get the same amount of information. Secondly, a competitive market often leads to confidentiality issues that add to the difficulty of collecting basic information. On top of this, we add to challenge the lack of resources and the fast turnover in staff. Energy data collection is a complex and costly process, and here we will give our types of data collection for energy statistics. First one is surveys. Countries can collect data by targeting all the units' population, which is called census, or they can use subset of representative units selected from the population, which is called sample survey. Censuses are more time-consuming and costly exercises, especially for collection of end-use data. There are two different types of survey depending on sampling units. first one enterprise and second one is household survey. Business registers and lists are used as a frame of the survey. International standards need to be taken account while designing questionnaire, such as for unit of measurement or definition of energy product and flow. Administration data. Administration data is the data collected for administrative purposes. It may be held by the government or by public-private company, and it can lower the survey burden. But it has dependence on third parties, so cooperation is needed among policymakers, administration, and statisticians. Now we will illustrate possible data sources and types of collection for natural gas. Broadly, there are two main sources for the gas data, from energy industries or suppliers on the supply side and the energy consumers on the demand side. For supply, data can be provided by energy industries whose activities directly relate to the production or some part of supply chain, and data are collected from energy producers through surveys or with administrative data. Import and export data are usually compiled through custom office. In general, natural gas production and distribution monitored for administrative purposes. By collaboration of various agencies within the country, we could have how much gas produced and distributed to the main consumer groups such as household or industry. It's important to adapt survey to changing consumption pattern. For example, natural gas consumption in transport and non-energy use reached almost 20% of total natural gas consumption in 2015, whereas it was only 5.5% in 1973. For demand side, to have detailed energy consumption data, end-use survey for household and enterprise need to be carried out. End-use energy statistics surveys are very important instruments for assessing energy consumption activities, tracking the potential for energy efficiency improvements, and helping to design our future programs and the policies. Data collection from energy consumers is complex due to diversity, mobility, and detailed question of forms. To have full picture of natural gas supply and demand statistics, integrated approach need to be used, and this involves using existing surveys such as household budget survey, direct measurements, and estimation and modeling to fill the gaps in the dataset. Now we are going to see how all these flows are transmitted to the IEA to produce international statistics. Our natural gas questionnaire has 5 different tables. These questionnaires are sent every year to the national administration for them to fill it with annual data. The first table has information on the supply of natural gas, production, total imports, export, and stock change. Then table 2 has the breakdown for the consumption. Tables 3 and 4 include trade by country, and we gather total trade and LNG separately. Finally, in order to improve our data to assess energy security, we're extending the table 5, where we collect information on gas infrastructure. This slide shows how different tables are interrelated within the questionnaire and also with the rest of the annual field questionnaire. The relations between tables allows us to do internal checks. In addition, the natural gas questionnaire is interrelated with other questionnaires by the transformation sector and the receipts from other sources. The receipts from other sources are included when they are blended into natural gas grid. This includes manufactured gases from the coal questionnaire, LPG from the oil questionnaire, and biogas from the renewables questionnaire. To understand how the questionnaire works, let's see 2 examples. Imagine we receive the following information for country A. 180 million cubic meters in standard condition of gas are produced from a gas field with a gross calorific value of 38,000 kilojoules per cubic meter, and 79,000 terajoules of LNG are imported from Algeria with a gross calorific value of 39,500 kilojoules per cubic meter. So firstly, we identified different pieces of information. We have a value in blue, units in green, the flow in purple, and the gross calorific value in pink. With this information, we need to fill an entire row of the questionnaire in the right. We can start filling the table with provided data, so we fill 180 million cubic meters into the row of non-associated gas, and we can also fill its gross calorific value. It's important to remember data in the questionnaire should be reported in MCM in standard conditions and terajoule in a gross calorific value basis. From the gross calorific value and the volume, we can calculate terajoules and we get the net calorific values by multiplying the gross calorific value times 0.9. Assuming this is the only gas produced in the country, we can also fill the first row of indigenous production. From the import data provided, we know the value on energy units and gross calorific value. In this case, we do the reverse conversion from energy units to volume using the gross calorific value. Finally, we sum the production and the imports to obtain the inland consumption calculated. Now it's a good moment to point out the role of statistical difference. As you can see, the supply balance is reported under calculated inland consumption. This is because ideal supply and consumption data should be from two different sources. In a perfect world, the result from two sources will be identical. However, this is never the case. And statistical difference is a good indicator of the completeness of the data. One last comment before moving to the next slide. As we only collect consumption data on energy units, we use the average gross calorific value for observed consumption to convert the data into volume. So this is a key figure for the countries to report. Tables 3 and 4 include the breakdown for the imports and exports, origin and destination. Here we could use the information on the origin and also differentiate if the trade was pipeline or LNG. In this case, we need to notice that LNG is reported as an of which item, so the pipeline imports are computed as the difference between the total and the LNG. Again, we use the gross calorific value to calculate the million cubic meters. Now, focusing a little bit more on trade statistics, we would like to highlight the fact that we collect data based on ultimate origin and final destination, which is different from the entries and exit criteria that you may find in other statistics, such as monthly gas statistics. To understand this better, let's use the example of Maghreb-Europe gas pipeline, which links the gas fields in Algeria through Morocco with Spain and finally with Portugal. Considering these measurements for cross-border flows, the countries should report as imports from Algeria the gas that is used in the country. 1,000 million cubic meters in Morocco, 8,000 in Spain, and 2,000 in Portugal. On the other hand, Algeria should report the same quantities to the destination countries. Often this represents a big challenge for some countries, especially after the liberalization of the gas markets and its regional integration and the increasing relevance of more flexible contracts. For this reason, we are currently working at the IEA to improve the trade data collection. After collecting the data through different tables, the data needs to pass through a data quality control, which will include arithmetical checks where we should look at sums, totals, signs, and we also check the consistency between tables in questionnaire and between different questionnaires. There are also statistical checks where special attention should be paid to statistical difference and the consistency of the time series. Among the physical checks, it is essential to check the calorific values, the comparison between the physical and energy balances and transformation efficiencies. And finally, we compare with secondary sources and we make sure that the data are complete and tell the correct story. We are approaching the end of this presentation and we have talked about the importance of natural gas in the world, about natural gas data collection and the validation, and now I would like to talk about the uses of data. The data collected by IEA have a multitude of uses. Outside of IEA, the data is used globally by governments, by academics, by analysts, investors, and other associations. And data can also be used to assess the security of supply, to compare between countries, to assess how effective policies are, and most to make sound policy and business decisions. The foremost use of natural gas statistics in the IEA Natural Gas Information Book. But natural gas data is also used to create energy balances, calculate the CO2 emissions, as well as energy efficiency indicators. The data are also used within the IEA to conduct analysis, develop forecasts, and they are also used to produce World Energy Outlook. The most commonly used statistic can be found in our easily accessible booklet, the Key World Energy Statistics, and the associated mobile application. Thank you for listening to us so far. If you want to learn more about the IEA Energy Statistics, we have a lot of different sources that can be helpful. You will find below the links for our Energy Statistics Manual, which is a comprehensive manual available in 10 languages. You can also visit the IEA Statistics website for a wealth of resources, including our questionnaires, glossary, and documentation related to our data collection and methodologies. Also, you can have a look at the United Nations International Recommendation for Energy Statistics, which provide a methodological framework. Thank you again for taking time to listen to us.